and I thought we would just go ahead and start officially. We mentioned on Monday two words that I'd like for you to know. One of them is called miscible, and the other one is called immiscible. Hey, can you hear me, Dana? Yeah. Okay. Right, so, anybody remember what immiscible means? What does immiscible mean? It does not mix. An example we gave was oil and water. So I went ahead and mixed some oil and water together. See what happens when you mix oil and water? Okay. This is not trickery. I brought some oil here, and I'll add some more water to it. I'll force it to mix. If I force it to mix, you guys think it will mix? No. Okay. So what we mentioned is that there's something about the water molecule that makes it very, very, antagonistic to the oil molecule. And there's something about the oil that makes it not want to be with the water. Okay, so let's do this again. I'll try my hardest to make it to mix. I ate at the cafeteria yesterday. They had salad with the salad dressing. Okay, it's kind of the same thing. All right, so no matter what, there's always a partition. Do you guys see this? There's a partition. The oil would rather be with the other oil, and the water would rather be with itself. Okay, so this is, as you guys mentioned, the best example of immiscible. Immiscible means does not mix. Okay. We also did another example and another word that I'd like for you guys to know, and that is miscible. Okay, so immiscible means cannot mix. Okay. Example is oil and water. Miscible means it can mix. Okay, so the example that we gave on Monday's class was ethanol and water. Okay, so I have some ethanol and I have some water, right? So just to show you guys, I have some ethanol here. Okay, ethanol is an example of a functional group. Okay, the functional group of ethanol is called alcohols. Okay, so I'll pour some. This is ethanol here. Okay, this is what's called qualitative, meaning I'm just throwing some volume. I'm not measuring the volume. If it was measuring like 10 mils or 12 mils or 50 mils, it would be quantitative, but this is qualitative. All right, so take some ethanol. I'll put some water in. Okay, what do you guys see happening? Okay, there's definitely a difference, isn't there? Okay, there's definitely a difference between the left-hand beaker and the right-hand beaker. Look, let me compare the two. Okay, you guys can clearly see immiscible versus miscible, right? Am I right? So we're going to say ethanol and water is an example of a solution, liquid to liquid. Two liquids, we're mixing two liquids together. And we're going to say they are miscible. Miscible. So in other words, they can mix. Okay, they can mix. Okay, the example that we're going to give here is ethanol and water. Okay, so there's something about the water molecule that would make it want to interact with the ethanol molecule. There's something about the ethanol molecule that would make it want to interact and dance and intermingle and, be with the water molecule. There's something about the water molecule that would want to make it get away. Okay, get away from the oil. And there's something about the oil molecule that would want to make it get away from the water and be with itself. Okay, that's the whole idea behind miscible and immiscible. Okay, when we join or add two liquids together. Well, let me give you another example here. All right, so we all had, except maybe for a small minority of students, we all had Chem 1 here. And in the last half of Chem 1, there was a talk about Lewis structures. Okay, Lewis structures. And this is the Lewis structure of ethanol. Okay, this ethanol molecule. Okay. Right, so the black is the carbon, the red is the oxygen, all the whites are hydrogens. All right, so this is ethanol. I'll write it out as CH3CH2OH. Okay, this is a functional group known as the alcohols. Have you heard this term, alcohols? Okay, when I say alcohols, I'm not talking about something that you go to the ABC store and buy. Okay, this is what in organic chemistry we call functional group. Okay, functional group. Okay, there's many functional groups in organic chemistry. In fact, I have a handout of some functional groups. You do not have to memorize them, but if you do take organic chemistry, you will have to memorize them. Okay, so before class you can take this and you can use this for the exam. And I'll give this to you after class. All right, functional groups. The functional group for an alcohol. Okay, the functional group for an alcohol is going to be this. The functional group for an alcohol is going to be this. Okay, don't worry about the R. Okay, don't worry about the R. That could be just an atom as hydrogen. It could be a whole bunch of atoms. We don't worry about the R. Okay, all alcohols are going to have the OH. Okay, anybody know what OH is? Okay, OH is called the hydroxyl group. Hydroxyl group. So don't worry about the R. Okay, it could be anything. Okay, but all alcohols are going to be unified by the fact that they have that OH hydroxyl group at the end. Let's go over some alcohols together. Okay, ready? Let's do some alcohols together. Okay, this is called methanol. Okay, how many carbons? 1. All right, ethanol, which is what we have over there. How many carbons? 2. Okay, how many carbons for 3? I'm sorry. What is 3 carbons? Propanol. Propanol, right? Yep. Okay, how about 4 carbons? Butanol. Okay. So we add another CH2 unit. 1, 2, 3. 4 butanol. Okay, anybody smoke cigarettes? Okay. Cigarette lighters have butanol in them. Butanol. Okay, so we're just adding incremental CH2 units. Okay, how about 5 carbons? What's 5? Pentanol. 1, 2, 3, 4, 5 pentanol. Okay, what's 6 carbons? Hexanol. 6 carbons is hexanol. Okay, what's 7 carbons? Heptanol. Okay. I think heptanol. Okay, so 6 carbons. Hexanol. Okay, moving forward, what will we get? Septanol. And then what's after that? Octanol. Septanol. Octanol. Nonanol. And then decanol. Okay, 10 carbons. What do all of these have, okay, in common? Okay, all of these have in common the OH. Okay, OH. Okay, the hydroxyl group. That is an alcohol. Okay, very specific alcohol that we used in our example over there is ethanol. Okay, and we found out that ethanol is miscible with water. Okay. All right, so here's the structure of the ethanol right there. Okay, highlighted in yellow. I'm going to do something to this. I'm going to change the atoms. Okay, I'm going to change the atoms. I'm not going to add any atoms. I'm not going to remove any atoms. Okay, I'm not going to add or subtract anything. Okay, so watch what I'm going to do. Okay, so there's no magic. There's no sleight of hand. I'm just going to move things around. So now I no longer have ethanol, right? Is that true? All right, now I have the oxygen right smack dab in the middle of the molecule. All right. So what I have here is a new molecule, and it's a new functional group. And that functional group is not the alcohols, but the functional group is the ethers. Have you heard of the ethers? The ethers, okay? So the ethers are going to be like this. Okay, while the alcohols are going to have the OH at the end, and don't worry about the R. Okay, the ethers are going to have the oxygen, ROR. To have that oxygen at the middle. Okay, this is another functional group. Okay, this is the ethers. This specific ether is called dimethyl ether. Okay, what I've drawn, or what we've constructed here. Dimethyl ether is the name of this molecule. Okay, this CH3 is called the methyl group. Okay, this OH is called the hydroxyl group. Okay, so just as like learning the grammar of chemistry. Okay, once you learn the grammar of any language, it becomes very easy. You become very proficient in it. So in order for us to become proficient in this, we just have to learn the grammar, and in this case, the grammar being the functional groups. All right, so let's look at this table together. Okay. So this is an alcohol, right? And the specific alcohol is called ethanol. Okay, this is an ether. Okay, the specific ether for this is called dimethyl ether. All right, let's look at the molecular weight. Let's just compare these two molecules. Before we compare them, let me ask you this question. Okay, how many carbons in ethanol? 2 carbons. How many hydrogens? 6 hydrogens. And then how many oxygens? 1. Okay. And remember, I didn't add or remove anything here, right? I just changed the atom's order, didn't I? Okay. So we'll do the same thing. How many carbons here? Okay, work with me. 2. How many hydrogens? 6. And then how many oxygens? Okay. So they're going to weigh the same. Okay, they're both going to be 46 grams per mole, using the numbers in the periodic table and adding them together. Okay, the melting point of this alcohol known as ethanol is minus 141, right? Or minus 114, fine. Okay, this ether has a melting point of minus 141, dimethyl ether. All right, but let me bring your attention to this. Okay, check this out. This is very strange to me. Okay, the boiling point, which is the temperature in which the thing boils, right? Gets turned into gas. For ethanol, it's 78.4 degrees. And look, it's 2 carbons, 6 hydrogens, and 1 oxygen. And they both weigh the same because, you know, it's just the same elements in the periodic table. But look at the boiling point for dimethyl ether. Look at that. Minus 24 degrees. Okay, they both have the same molecular weight in grams per mole. They both have the same number of carbons, hydrogens, and oxygens. In fact, didn't I just change things around? I didn't add or subtract any atoms. So what gives? Why does one have a boiling point of this much, and why does the other one? It's the same thing. Maybe it's a different functional group. Why does this have such a drastically lower boiling point? Okay, furthermore, taking the same ethanol, why is it that it's capable of interacting and mixing with water, this alcohol? And why is it something like oil does not want to mix with water? Okay? We also have to look at the structure of water. Okay? Let me give you the structure of water. Okay, water is not linear. Okay? Water is bent. So water, for someone who teaches biochemistry, or if you ask any biochemist, water is the most amazing substance on the planet. And there's people, scientists, who spend hours talking about water. And, you know, there's a conference where they always talk about water. It's the keynote speaker talking about water. Okay, water is 70% of our cells. It's 70% of our bodies. It's 70% or so of our planet Earth. How many of you have had an MRI done or any type of imaging? Imaging. So what are you imaging when you have an MRI done? Okay, you're essentially imaging water because water is magnetic. Okay, so that's the basis for radiology. So water is just this fascinating and amazing substance. The structure of water is this. Okay, you have a hydrogen, oxygen, and hydrogen. We have 2 lone pairs. And the structure is bent. Okay, bent. So this bent molecule wants to be with itself and get away from water. This bent molecule wants to mix with the ethanol. Okay, why is all of this? Okay, why all of miscible, immiscible, and why such a different boiling point for 2 molecules that are essentially the same? Same carbon, same hydrogen, same oxygen. Okay, it all comes down to intermolecular forces. Okay, IMF. IMF, intermolecular forces. Okay. So there are several different types of intermolecular forces, and I'm going to go over those right now with you guys. I think there's about 3 or 4 that I want you guys to know, and we'll have a lab on this 2 weeks from now. Okay. All right, I'm going to move on to the next page. Is that okay? All right, so we're going to focus on liquid to liquid. All right, so ethanol to water, oil to water, dimethyl ether to water. Okay, so our focus is going to be on liquid to liquid, the phases. You could have solid to liquid, okay, air to liquid, but we're going to focus our attention on liquid to liquid. Okay. All right, shall we go over some of these? All right, let's go over some of the main intermolecular forces. This is like the main focal point of this chapter and today's lecture. Okay, this morning's lecture. All right, the strongest intermolecular force is ionic. This is the strongest. Okay, you remember ionic compounds from Chem 1? What is an ionic compound? Okay, what do we know about it? So we can't forget what we learned in Chem 1. Okay, don't forget. Okay? Okay, don't forget. What is an ionic compound? Ionic. What is it? Okay, very good. It's a metal and a non-metal. Excellent. So what happens in an ionic compound, thank you, Armani, it's a metal with a non-metal. What happens is that you exchange electrons. So this is a complete and total exchange of electrons. I give 1 electron and you take it. Or I give 2 electrons and you take it. Okay? So there's a giver and a taker, and we're giving and taking away full, total, complete electrons. 1 electron, 2 electron, 3 electrons, whatever it may be. So this is a full electron transfer. It's like you're giving it, it's an exchange. Okay, full, not partial. This is not a bond, it's partial. This is like, here, take it, and you grab it. Okay, right? And that's the strongest. Let me give you an example of an ionic compound. Everybody knows salt. Okay, what is salt? Sodium chloride. Okay, so it's Na plus and Cl minus. So we do what's called a switcheroo. You switch. Okay, you switcheroo. This is how I teach it. So, okay, the +1, just the number, the +1 goes here, and then the -1 and the 1 goes here. You switch, and that becomes NaCl. Okay, so this is a very strong ionic compound. Okay, an ionic bond, if you will. Full charge transfer. If you look at sodium chloride under a microscope, it actually looks like a lattice. It takes a lot to break up that lattice. Okay, it looks like this. If you take a very powerful microscope and look at crystals of sodium chloride, you know, crystals, right? It takes a lot to break up a crystal. Okay, it's this tremendous organization. Okay, there's this tremendous lattice organization. This makes ionic compounds the strongest IMF. Okay, this makes ionic compounds the strongest IMF. So, intermolecular force. So on an exam, if you see an ionic compound, which is metal and non-metal, okay, will it be the strongest intermolecular force or the weakest intermolecular force? Strongest. Okay, so ionic compound, strongest. Okay, you need to know that it's an ionic compound, right? Okay, so here we're looking at a very, a lattice. What is a lattice? Like brick in a brick house. Okay, they're organized in such a way. Okay, that's a lattice structure. Okay, so ionic compounds have a lattice. All right, so that's the strongest. All right, let's go to number 2 and 3 here. Number 2 and 3 together, 2 and 3 are called polar compounds. Okay, so ionic compounds, you just want to think of a lattice. It's a very strong organization. Okay. Just look at sodium chloride in a crystal or in a microscope, and you'll see what I mean. Okay, or any ionic compound. All right, both 2 and 3 are called polar compounds. We have hydrogen bonding and then dipole-dipole, which is also polar. Okay, so what is all of this? All right, so first of all, hydrogen bonding is part of a polar compound. Okay, London dispersion forces is part of a polar compound. Okay, they're all in the same category. They're all in the same category, but this is just a special type. Okay, hydrogen bonding is a special type. Alright, so here what we want to do is, let me just give you the brief thing here. Okay, when you have something that's hydrogen bonding, okay, it's a very strong attraction. That's number one. Okay, stronger than normal dipole-dipole, even though they're both polar. Okay, they're both polar. Number two, this is not, as Armani said, metal, non-metal, ion exchange. This is partial charge interacting. Partial charge. It's not the full electron. It's not full. Okay, it's partial charge interaction. Okay, the key word here is partial.
For just hydrogen or for both?
For both. Remember, these are the same categories. KC, right? These are the same category. Okay, I want you to know that polar compounds include hydrogen bonding, which is stronger, a little stronger than dipole-dipole. Okay, this is important. So partial charge interaction. You can't see that. Now you can see that. I was writing in thin air, right? No, I was writing right here. Okay, so it's a strong attraction, not a full bond, it's attraction. Okay, so if we attracted to one another, we're close to one another. It's not like we're like this, okay? We are attracted, okay? So there's an attractive force, all right? And it's a partial. It is not. Here, Armani, take the 2 electrons. Okay, I'll take them. BJ, no, it's not an electron exchange. It is a partial electron attraction. So I have a partial positive charge, and you're partial negative. What happens? What happens? We attract. Not full. A full positive, full negative, what happens? They attract. What about partial positive and partial negative? They also attract. Do they attract as strong? No, not as much. Still strong, but not as much. Okay, so a partial positive with a partial negative. Okay, so for hydrogen bonding, you're going to look for 3 things. Okay, look for 3 things in the molecule. You're going to look for an OH. Okay, you're going to look for an NH. And you're going to look for a fluorine. Okay, if you see those 3 in a molecule, okay, OH, NH, and F, then that molecule has the potential to hydrogen bond. Okay, OH, NH, and F, fluorine. We don't see in biochem, we don't see fluorine a lot, but fluorine can hydrogen bond. So this is what you want to look for in the molecule. An OH anywhere, an NH anywhere, or a fluorine anywhere. Okay? Okay, we'll talk more about this on Friday's lecture. So let me show you water. Let's talk about water here. Page 3. I'm going to go to the next page. Okay, let's talk